So good afternoon, everyone. Welcome to the third lecture of this mini school. And Jan will tell us everything about the simulation of steel unitary systems, but we're slowly coming to the open quantum systems.
Okay, thank you, Ilya. Good afternoon to everyone once again. Okay, as promised last time, today we're going to talk a bit about the more novel methods for simulating closed quantum systems. Okay, so slide. So in today's lecture, we're going to talk about something called post-Trotter-Suzuki methods for Hamiltonian simulation. So in the previous lecture, I spoke about the Trotter-Suzuki product formula methods for simulating closed quantum systems. And these were developed, so Suzuki developed these methods around the 80s and early 90s. And formally, the rigorous error analysis that was done with these methods was done around the 2010s. And since then, people have constantly been looking for more efficient and optimal methods for simulating closed quantum systems. Okay, so today we're going to discuss two of those methods. So there's been many different methods that have been developed, some of which rely on a quantum walk-based approach. Some rely on constructing something called multi-product formulas. In today's lecture, we'll discuss one that relies on just implementing the direct truncated Taylor series to implement the time evolution of our closed quantum system. Okay, and the main reason behind why we searched for these methods is because we were interested in looking for methods that can improve the precision of our simulation, as well as giving you a better gate complexity. And by that, I mean improving the complexity and how the algorithm scales complexity-wise by reducing dependence on things like the size of the system, the dependence on the norm of the Hamiltonian, as well as the polynomial dependence on time. So if you remember in the previous lecture, when we spoke about product formulas, we see that only in the order of the Suzuki-Trotter product formula tending to infinity do we get a somewhat linear dependence on time in the scaling. However, for any practical implementation of product formula, you're never going to get a linear dependence on time. The time scale with respect to order k is 1 plus t to the power 1 plus 1 over 2k. And this scaling means you'll never achieve a completely linear scaling in time. And of course, to get optimal time complexity scaling, you want a linear scaling with time. So the idea here is that people develop what we call post-Trotter-Suzuki methods in search of, as I said, improving gate complexity and improving the precision with which you can simulate the time evolution of the closed quantum system. But what I should mention is that these improvements come at a cost. And the cost that they come at is, of course, whereas previously when we used the Trotter-Suzuki product formulas, we had deterministic implementations, meaning before we created before we run our algorithm in a quantum computer, we already know what the gate set is going to look like, and we know what we expect the output to look like from our quantum circuit. However, by achieving some of these improvements in precision and complexity, the implementation sometimes now becomes probabilistic. And by this, when I say probabilistic quantum algorithm, I'm not referring to the probabilistic nature of quantum computing, but I'm referring to something where the output of our quantum algorithm has a probability of success and a probability of failure. And this is what happens when we start to look at these more advanced algorithms that we're going to talk about today, is that we have these caveats that are built in, that now the implementations become a lot more complicated than just using a product formula to decompose our unitary evolution into just simpler unitaries and implementing them as a gate set. So there's going to be some caveats, but we'll talk about it. Okay? So in this lecture, and the slide is not for reading now, but it's for when the slides go up after, we're going to talk about two important post-Trotter-Suzuki methods. The first one being the Hamiltonian simulation by truncated Taylor series. So if you remember in last week's lecture, when we spoke about product formulas, we started with the point of expanding the time evolution operates in a Taylor series. And I said, wouldn't it just be convenient if we could just truncate this Taylor series up to some order and then just use that to approximate our time evolution operator? And the reason why we didn't do it last week was because I mentioned that we wanted products of unitaries because they're easy to implement. And we'll see today why doing the truncated Taylor series is difficult, but it's still possible. And we'll see as well the improvement that it gives. So you see the references here on the slide. As I said, this slide is not for now, it's just to give you the references. So when the slides go up online, these are the papers that you want to look at if we're talking about Hamiltonian simulation by truncated series. And these are the papers I used to put together the slides. The second method is, in fact, a very, very important one. And I'm talking about it only in the context of Hamiltonian simulation, but this method that I'm going to talk about is so general that there is a paper that says that you can use this method to unify all quantum algorithms. And the method is called quantum signal processing and qubitization, and its more general form, which is the quantum singular value transform. But this method is going to rely on us performing a type of spectral transformation, to do the simulation of our time evolution operator. And I'll get into more detail. This method it's a bit of a complex method, but currently it is one of the methods that give you optimal scaling both in time and precision for your complexity. And I think as far as Hamiltonian simulation goes, this is the optimal method to use to do Hamiltonian simulation. And it's because of its optimality, it's found its way into other aspects of quantum computing and quantum algorithm development to provide the same optimality in those settings as well. But here we're only going to look at it in terms of just simulating Hamiltonian dynamics. Okay? And something else that I see another word here, qubitization. Qubitization is a process that's going to allow us to perform this quantum signal processing on a single qubit, but have it transform the spectrum of an operator acting on a larger space. So this idea of qubitization is to be able to map high-dimensional systems to transformations on a single qubit. And we're going to see how useful this is when we do Hamiltonian simulation. And these are all the references that we're going to need to understand this method of Hamiltonian simulation by quantum signal processing. It's a bit of a rabbit hole, I should say. You want to learn about quantum signal processing, and you find out there's 50 papers that you need to read to even grasp the concept. But I've tried my best to just distill all of that into just a few sources that you need, just to get a basic understanding of the power of this algorithm. Because this algorithm doesn't just allow you to simulate Hamiltonians, but in fact, in its more general sense, it allows you to realize polynomial functions of operators on a quantum computer, which is extremely useful for many different quantum algorithms and solving other problems with quantum computers. So let's start by talking about Hamiltonian simulation by truncated Taylor series. So of course, by now we know what the simulation problem is, so I'm not going to go over that again. But we'll talk about just very basically, let's consider the Hamiltonian of a d-dimensional system. Okay? And for now, let's just let this d be some power of 2, so 2 to the power n. The reason why is that qubit systems are easy for this, but you can always take any CubeSat or qubit system and pad them so that you can fit it into a qubit system. So now assume that the Hamiltonian acts on a bunch of qubits. Okay? And we can always write the Hamiltonian that acts on a system like this in the following form. We can write it as a sum of real numbers times HL, where HL is Hermitian and unitary. And because of the type of restriction that I put on the dimension D, HL is just going to be tensor products of Pauli operators. Okay, so it's just going to be a string of Pauli operators that are tensor producted together, each one acting on a different qubit. And you can construct a basis like this to write H in. It's completely valid and it's allowed. And it's going to make our life a lot easier. So of course, there's a more general way to consider this, and there's other bases that you can use to construct this HL. The generalized Pauli basis will be one of them. But I won't talk about that here. We'll just use strings of Pauli operators because they're easier. Okay? So this is going to be the form of the Hamiltonian that we're going to consider, and there's capital L terms inside of this Hamiltonian. So that's this uppercase L is referring to the number of terms in our Hamiltonian. Okay? So if we consider the time evolution operator that we've been simulating the last two lectures, is u of t is e to the minus I h t. We know that we can write it as a Taylor expansion. This is known stuff. Okay? And we can approximate this by a truncated Taylor series, meaning that if we write this as a Taylor expansion and we decide, let's stop this series at some finite term, then we call that a truncation. Don't know what that means. It means that this is an infinite series, and all we've done is at some point in the series we cut it and we make it cut. So that is what we mean when we say truncated Taylor series. And I'll say up to order uppercase K. So this capital K is going to be the order in which we truncate our Taylor series. And if we do that, then we can approximate our time evolution operator by this u of tilde, and the Taylor series now, instead of being infinite, it just stops at some capital K. Okay? This is a straightforward thing you would have done in your first year calculus course, or even some course on numerical methods or something or other. But for large enough K, this approximation we know is going to be very, very accurate. However, as I've mentioned in the past two lectures, for large enough is not good enough when we're doing quantum simulation. You need to have an actual bound of what K should be. How does K scale? And it should be usually given in terms of the precision. And we'll see why this K is so important. If you remember when we did product formulas, we had a number n, and n was how many times we split up the time interval. And we wanted to see how n scaled so we can figure out how many steps we needed to do of our Trotter product formulas. Well, here, I didn't do that. You might notice I didn't divide t into small sub-intervals. I just left it just as it is, and I made the expansion. And I'm going to be interested in K because K is going to govern how many terms in here I need to implement for me to implement this product formula. I mean, sorry, this truncated Taylor series. Whereas n told us how many times I needed to implement the product formula, K is going to tell us how many terms in this truncated Taylor series that I'll need to implement, okay? So we need to bound the error, and by now, I think everyone here should be an expert on bounding error in these things because it's so straightforward, okay? But effectively, if we take the norm of the difference, we know because we started out from the Taylor expansion of u of t and we chopped it after order K, we know that up from 0 to K, all the terms will cancel exactly. So all we're left with afterwards is just precisely this, just the error term, okay? And we're left with this error term here, which is just going to be from K plus 1 to infinity, you just cap off. What you do is you then use sub-additivity and sub-multiplicativity to take everything in. Okay, you use that to just take everything in. And we're left with this, where we just have the norm of the Hamiltonian. And I'm not going to bound the norm of the Hamiltonian because I've shown you how to do that, and it's not going to help us with our analysis here for me to give you a bound on H. We just leave it as it is. And once we're done with this, we can then use a result from last week's lectures, which told us how to bound the tail end of the Taylor expansion of the exponential function. And we found that we have this bound here. And we see already that the error is bounded by a prefactor, which is e to the t on the norm of H. Okay? And, as I mentioned last week, we don't like exponential factors when we have complexity scaling because it means that, things are going to be very, very blowing up quickly in terms of our complexity. So what we can do is we need to bound this above by our precision and then solve, okay? We're going to solve. So we'll solve for K. And that's an extremely, long and arduous process involving Stirling's approximation and some approximations of the log function, which you can look at in those references that I put on the first slide. But I will just simplify it and just write down how K scales. So K scales in the following way. It has a logarithmic scaling on this argument divided by epsilon, which is your precision, which you choose beforehand, okay? And this already is a pretty good scaling. We don't have any polynomial scaling. So there's nothing that's growing, as it increasing as squared or cubed or quartic or power 5. It's logarithmic scaling, so that's already a positive. However, we see that we got these quantities like norm of ht. And that's not something that's important at the moment, because the simulation time will usually be specified beforehand, so it'll be constant. And the Hamiltonian is also specified beforehand, it's also constant. So we can rewrite the scaling for K by just dropping everything out. K scales like this with respect to the precision epsilon. Okay. So if we want to simulate the time evolution operator up to a precision epsilon, then we use this. Usually we just take the ceiling function of the quantity that's inside here, and that will give me K. And then that's the order at which I truncate my Taylor series. Okay. Now, that's all well and good, but what is the process? What is the complexity of performing the full simulation? This is just telling us about K. So how do we do that? So what this tells us is, for some fixed time T, with this complexity for K, okay, if we reduce the precision to epsilon over T, right? So we take the precision, and instead of the precision just being 10 to the minus 5 or 10 to the minus 6, we'll then reduce it even further by dividing it by the simulation. And then we repeat the process T times. So that's why I say big O of T times, because it's linear in T. Then we get the total simulation complexity of the algorithm that looks just like this here. It's precisely like this, but I've replaced epsilon with epsilon over T. And because I repeat the whole process T times, I end up with just a prefactor of a linear T. And this is the same as me dividing the interval into n steps. This is exactly the same procedure of me dividing it into 10 steps, but into n steps. But instead of doing it in the beginning and using that lemma that I showed you last week, which relates these n implementations of some algorithm to a bound which is like n times the difference between a small evolution time, this just circumvents that whole procedure. And it just means that if we just reduce the precision and then repeat the whole process T times, we get a linear scaling now in time. So already we're better than the product formulas, because product formulas will never reach linear scaling in time. So already, although yes, we don't like products in our complexity because it means things grow a lot faster, but it's linear in T, which is a lot better than having something like T squared or even T to the 1.5, so on and so forth. Okay? And this will be the complexity of the truncated Taylor series algorithm, and this will produce for you an output state or approximate unitary up to a precision epsilon, which you choose, of course. So this is just some formal discussion about the complexities, right? But how does it look compared to what we did last week? So here's some plots, right, that I just made, plotting those complexities from the previous week and now, this truncated Taylor series. Remember, I didn't even tell you how we're going to implement the Taylor series yet, but just from the analysis on the complexity and how it's scaling, let's see how much better it is. So this is log 10 in complexity. Okay, so these numbers are very, very large. Here you're looking at 6 million, 5 million, these are big numbers. Okay, and this is telling you how many steps of your algorithm you need to implement. And if you look here, for the number of terms in your Hamiltonian being 5 and a precision of 10 to the minus 3. So what I've done is I've chosen the simulation time from 0 to 10 seconds. I've varied the number of terms in my Hamiltonian, but I've kept the precision the same, always 10 to the minus 3. This is just a standard precision that you'll find in most literature. And let's look at the complexity, so the log base 10 of the complexity, right? If you look at the first order Chomsky formula, you see that for 5 terms in your Hamiltonian, it's going to have the most steps. And then the second order improves a little bit on that, and the fourth order is going to improve a bit on that even more. But the truncated Taylor series is drastically improved. And if this is a difference between, it may look like, okay, it's 1 and that's 6, but it's a difference between 1 million and 6 million, which is quite big. Okay? And then if you look at here, I've done the same thing, but just with L is equal to 30. And with L is equal to 30, you see, oh, okay, something else happens now. And this is the problem with the Trotter-Suzuki product formulas. To get to a high enough order using the product formulas, the complexity has a prefactor, which is exponential in the order. And what happens here is that as you go up in order and the system size increases, you find that the higher order formulas require more steps to get to the same accuracy than the lower order formulas. So already you see, with just 30 terms in your Hamiltonian, the fourth order formula is already, performing the worst in comparison to the first and second order, which is here. So if I want to approximate my evolution up to fourth order, and there's 30 terms in Hamiltonian, it means that I'm going to need, so many more steps to get to that order. But what happens here? The truncated Taylor series, because it doesn't depend on the system size, because of course I said that the norm of the Hamiltonian is fixed, you can remove it. It doesn't have a direct dependence on the system size. What ends up happening is that the complexity only scales with precision. So it doesn't matter how much I change this L, it's only governed by the precision and the simulation time, which is linear in the simulation time. And because I'm taking the log, that's why you're seeing this logarithmic curve here. So what this means is that this truncated Taylor series outperforms your standard trotter product formula, right? And you can see it's not just a small outperforming, it's quite large, okay? But of course, as I mentioned, it has its caveats, because you can see here, L is equal to 120, the gap between the fourth order and the second order and even the first order is getting so much more larger. So this is the problem that you have with product formulas. The complexity just scales so poorly with the system size. But truncated Taylor series seems to solve that problem, okay? Now let's talk about how we can implement this, because it's all well and good. I showed you these nice plots, but you need to see the caveat, and the caveat comes from the implementation, okay? Because it's not so straightforward to implement the Taylor series on a quantum computer. So let's start by looking at our truncated Taylor series. We know H was just a sum of terms, right? So you have a sum of terms to some power k, and this you can use some simple algebra and some summation notation to rewrite in this following way here, where you have k sums, and you have products of the Hamiltonian here. And you can replace all of this, this should be a capital H. You can replace all of this by just the sum here, where beta j is just real coefficients, and bj is just a unitary, okay? So it's just some unitary. And these correspond precisely to this operator here, and beta j are just the respective coefficients. So if I want to implement this u tilde of t, what I need to do is I need to implement a linear combination of unitaries, because that's what I have to do. And this m here, there's just m terms in the sum. M is going to be whatever number you get after evaluating the sum. I won't have this, I didn't put an explicit calculation, but it's going to be all the terms here that correspond to beta j and. But the main idea is that we have to implement a linear combination of unitaries. Now, so far, we looked at product formulas because we said it's natural to implement products of unitaries in quantum computing. That's how you do quantum computing. It's products of unitaries. But now, for us to do this type of simulation, we need to do a linear combination of unitaries. This is a sum of unitaries. So it's no longer just a straightforward, u1 times u2 times u3 and so on and so forth. It's a linear combination. So how do we go about doing this? So the question is asked, how can we implement a linear combination of unitaries, right? So if I take two unitaries, UA and UB, we know that their product is once again unitary. So it means you can implement this on a quantum computer fairly straightforward. However, when we consider a linear combination in the following way, where kappa is just some positive real number, and we just take the sum, we want to implement a linear combination like this. We see immediately we have a problem. This is not a unitary operator. And you can check for yourself if it's a unitary operator or not, but you'll see that it's not a unitary operator. So you can't directly implement this on a quantum computer. If this whole thing was unitary, then it would just be one block that you're going to implement in your quantum computer. But this is not unitary, okay? So we can't directly implement it in a quantum computer. However, there is a procedure that we can use that will allow us to implement this on a quantum computer probabilistically, meaning there'll be a probability that we succeed by implementing this and a probability of failure that we don't implement this, okay? And we can do this with some quantum computing techniques. So let's discuss the procedure. But if you want to learn about where this procedure was done, there's the reference down here. This is also another method for simulating Hamiltonian dynamics. which relies on something not called the truncated Taylor series, but something called the multi-product formula. But I won't talk about that here because the analysis is very, very complicated. So let's discuss how you can do this. So, as I said, there's no deterministic way to do this, but we can do it probabilistically. So if we define the following unitary operator, V kappa, which is a function of this kappa, in the following way, then we can construct a circuit, which I'll show you on the next slide, which will implement an operator proportional to this linear combination when we have an ancillar qubit, which is in the state 0, and the circuit will fail to implement this with the probability given here. So there'll be a probability of success to implement this linear combination and a probability of failure to implement it. So if I show you the circuit, right, this is the circuit that we have here. And as you can see, we have our system, which is represented by psi. We want to apply this linear combination of unitaries to psi. So the way you go about doing it is you have an ancillar system, which is just a single qubit. You apply V kappa to this, which rotates this. It will rotate this, this initial state 0 here. And then, depending on what are the probabilities or the amplitudes of this ancillar, you implement whenever this is 0, UA, and you'll implement whenever this is in 1, UB. Okay? Then you undo the transformation that you did. You apply V kappa again with dagger. So you uncompute that transformation. And then we post-select our output state whenever the ancillar is in the state 0. So whenever the ancillar is in the state 0, we will get back precisely this linear combination acting on psi with some prefactor, right? And when you take the probability or the absolute value squared of that amplitude, you will get the probability of success. However, there is also a chance that this state here is in the state 1. And when it's in the state 1, that is when your algorithm has failed and you don't implement that linear combination of unitaries. So we can do linear combinations of unitaries on a quantum computer. However, it's at a cost of it being probabilistic, meaning there is some chance that we can fail, that our algorithm will spit out the opposite of it, so the difference of these unitaries or something else altogether. However, there's been modern techniques that have been developed that are able, and these techniques are called robust and oblivious amplitude amplification. So just like what you did in Grover's algorithm, where you increase the amplitude of the state that you were looking for, you can increase the amplitude of the ancillar being in the state 0. And by increasing that amplitude, what happens? When you eventually post-select, you are guaranteeing that you get the ancillar being in the state 0, and which means you'll return your linear combination of unitaries. Okay? So let's generalize the idea to implement our linear combination of unitaries, right? So this idea that we have there is, it's all well and good for UA and UB, but we have our own linear combination of unitaries, and we need to implement that. Okay? So let's define a unitary operation B such that B acting on a register of qubits that are all in the state 0, and the number here is ceiling of log 2m, m because m was the number of states, or the number of terms in a Hamiltonian. And let's prepare the following state here. Okay, we'll prepare the state here, which we call beta, and beta is just this state here, B acting on a register of zeros. And what is the state? This state, which we'll prepare, is going to encode sort of the coefficients that are going to be in the linear combination. That's all the state is doing. It's encoding the coefficients of our linear combination, so that when we eventually do the post-selection, these coefficients go in front of the respective unitaries that belong in the truncated Taylor expansion. Okay? And this quantity S is just defined as the sum over the absolute value of all these coefficients beta j, which I expanded here for you so you can see the relation. And it's precisely just like a Taylor series of a truncated Taylor series of an exponential function with the argument t and the sum over the absolute value of the coefficients in the Hamiltonian. So S is kind of like a truncated Taylor series for exponential with this argument. Okay. Now, if the initial state of our quantum computer is going to be in the following register, where 0 is just a register of qubits all in the state 0. Again, we have taken this with sealing of log 2m, and psi is the initial state of our system. Then we can define an operation that we call select v. Okay? And what does select v do? Select v is just this unitary operation. And all it does is whenever the first register is in the state j and j, it will apply vj. That's all it is. It's kind of like a large operation that's applying controlled vj gains. That's all it's doing, right? And it's taking the sum of those, right? And then we can define the following operation, which will just be v dagger, select v, and we claim that this will implement u tilde of t whenever we measure the ancillary register, which is the first register, in the state 0 hat, meaning whenever we measure the ancillary register in all zeros. Okay? And after you do a little bit of algebra, which you can follow here, it's not very complicated. All we're doing is we're applying the operation W to our initial register, and we are taking the inner product with the first register being in the state of all zeros. Okay? And once you do this, you do all of the algebra by applying each operation. You first apply B, then you apply select, then you apply B dagger. You actually see that the output state that you get here is going to be 1 over S on u tilde of psi. Okay? That's what you get. So you've effectively produced the truncated Taylor series acting on your initial state, but it's proportional by some prefactor, which is 1 over S. Okay? Now, if after doing the post-selection, we get the desired result, but this post-selection will only succeed when with the probability 1 over S squared. Okay, this post-selection only succeeds with that. So, for example, if S was 2, then you're only going to succeed with probability 1 over 4, which is not very, very good. Okay, so we need a way to improve the probability. But before we do that, this is what the circuit will look like. You have the state of the system, you have all of the operators V, you have V preparing this register, and the select operation you can see is just doing this control operation, controlling on each of the qubits. And then you post-select by measuring only this register. Going back to thinking about something like Grover's, you see that we can increase the success probability by using this amplitude amplification strategy that I was talking about. So if we look at what W does to our initial register, it produces something like this, where this phi is some state that's supported in the subspace orthogonal to the ancillary register being in all zeros. So, so that's easy, right? It's just all the other orthogonal states. We can boost the chances of success by applying a reflection about the subspace spanned by everything in the state 0. The reason why we need to do the reflection about this state is because usually in Grover's, you do the reflection about the solution, but we don't know what psi is going to be here to reflect about it. So instead, what we will do, we'll reflect about the 0. And they call this a type of robust amplitude amplification. And you can do this reflection by using the following operator, R. And again, after doing a little bit of algebra, you see that you get this quantity here. But because u tilde is close enough to unitary, we can approximately say that u tilde dagger on u tilde is identity. And you get the following output state, where this is the new amplitude that you have. Okay? So you have this new amplitude that's there, and you see that, of course, you need to square this if you're going to get the probability. And if you just put S equals 2 again, what we've done is we've boosted the amplitude from 1 over 4 to now just 1. So the probability of success has been increased to 1. Because if you look at this integer is -1. So take the absolute value squared, you get probability of 1. Okay, so now we've taken something that was probabilistic in nature, and we've pushed the amplitude so much that we've pushed it to 1. But that's only for S equals to 2. Now, S can be other numbers. So how do we then push it to 1? Well, you can treat everything inside here, WR, W dagger, R, and W, sort of like the Grover iterate. You just keep repeating this set of operations, and that will keep pushing the amplitude closer and closer to 1. So that's how you can keep iterating this to get a more successful truncated Taylor series algorithm. Okay, so that's basically all I want to talk about for truncated Taylor series. I'll move on now to talking about quantum signal processing. So because here we've already discussed how to implement it, what the circuit looks like, and then how to use amplitude amplification to get a higher probability of success. And I've shown you how the complexities for this algorithm scale a lot better than the product formula approaches. Okay, now we'll describe the powerful framework of quantum signal processing. So these are the two most important references for quantum signal processing. It was developed by G.H. Low and Chuang I.L., and this is the same Chuang from Nielsen and Chuang. If you're curious, and they developed this process or this algorithm called quantum signal processing, and then qubitization, which they showed in these two papers how you can use it to do optimal Hamiltonian simulation. So the idea here is that given an operator represented by something which is called a block encoding, we can encode spectral information about it in a qubit through the concept of qubitization and then transform it. So we transform that spectral information by using quantum signal processing to implement a function of a block encoded operator. And this is the main idea behind quantum signal processing, is that we start out with something that is block encoded, we encode its spectral information into a single qubit by qubitization, we apply the signal processing procedure, and then we have the function or a polynomial function of our block encoded operator. And if we apply this method to the Hamiltonian simulation problem, using the method of oblivious amplitude amplification, which we already discussed, which will boost the amplitude of our block encoded evolution, this approach that that's mentioned here is what they've used to develop optimal complexity for Hamiltonian simulation. So even though there's all these trade-offs of probabilistic implementations and these more fancier quantum circuit implementations, the optimality in the complexity is worth the trade-off. And that's what they showed here. And I just want to make note that you see this process of amplitude amplification. If you've done a course in quantum computing, or I even teach it in our quantum computing course, which is we teach Grover's algorithm, we teach amplitude amplification. And there it looks very, very useful. But you look at how people who work in this field have taken a subroutine from another algorithm and have used it to do things like increasing the amplitude of the success probability of your quantum algorithm and use it in Hamiltonian simulation. So when you're thinking about these things that I'm talking about, don't only think of it in the context of Hamiltonian simulation. Functions of operators and being able to implement them on quantum computers are very, very useful and probably could serve a use in the field that you work in or even in the future field that you decide to work in. Okay. So let's talk about what is block encoding, because I use the word block encoding, but you may not know what is block encoding. But block encoding is very, very simple. If we have a unitary transformation view, we say that it's a block encoding of an operator A, right? And usually this operator A is Hermitian. It doesn't need to be Hermitian, but in our case, it's going to be Hermitian. But as I said, it can be in general any operator. And it's block encoded if you place A in the first block of a block diagonal matrix segments, right? So just a block of matrix segments. And you can write this using your bracket notation in the following way, where this 0, 0 is going to denote the first computational basis state of the ancilla register. Okay. So we can also equivalently write, instead of writing it in this way, we can also write it like this by sandwiching U in between these two operators, which extract out just A. That's all it's doing. Okay. That's what you see here. So something we observe is that for A to have a block encoding like this, A must satisfy that its norm should be less than or equal to 1. Okay? And we can also consider something called a scaled block encoding. So a scaled block encoding is where you have an operator that's multiplied by 1 over a scalar. Okay, and scaled block encodings are very, very nice because in some cases you may want to implement, half of an operator, half times an operator. So you want to be able to encode that nicely. So we need a condition for doing scaled block encodings. And the condition is that for the scalar being bigger than or equal to the norm of A, we can think of this alpha as a parameter that measures the quality of the block encoding where smaller values are better. Okay, so that's what the scaled block encoding does. For us, the scaled block encoding is important because we'll see later on that one of the requirements for the quantum signal processing theorem is to have your function of your operators being bounded. And when you want to do quantum simulation, that function is not bounded correctly, but we can just multiply it by a scalar, 1 over a scalar, and scaling it so that it's bounded within the right interval. So we're going to see that later on, but that's why the scale block encoding is so important to us right now. Okay. Okay. Sorry. Yeah. Okay. Okay. So a key problem is to transform a block encoding of one matrix into a block encoding of a related matrix. So effectively what you want is that if you have a block encoding of A, you want to produce a block encoding of f of A. Why do you want block encoding of f of A? Is because you want to easily extract it once you're done. You don't want to have f of A being all over the place in the matrix. You want something that's okay, A is in one corner of the matrix. After I transformed it, f of A is in the other corner of the matrix. Is easy to extract. That's the logic behind why you want something else that's blocking. And we also want to know what is the cost of doing this procedure. Okay? And this is the problem that's addressed by quantum signal processing. And I'm going to talk about it now independent of Hamiltonian simulation. I'm going to talk about it independently of qubitization. We're just going to address the simple problem. I have an operator A in a block encoding. I want to find an operator f of A also in a block encoding. And I want to know what is the cost of doing it. So we're building up the idea of quantum signal processing, and it's going to be a small chunk in doing the Hamiltonian simulation, but we'll talk about it in general. So we'll talk about how to do a transformation like this for a 2x2 matrix. It's very simple, 2x2 matrix, okay? The result of this is the core of the quantum signal processing concept. And the reason why we only need to talk about it for 2x2 matrices is because of qubitization. It's because when we get to qubitization, we see that no matter how high the dimension of our space, we'll always only do signal processing on a single qubit, and the qubitization is handling all the other stuff in the higher dimension. Okay? So let's talk about the quantum signal processing problem. So if you consider a single qubit rotation, which we'll call W of x, which is defined like this, right? This is just a 2x2 matrix, and it's a rotation where x is the argument rotation angle, and you can always write this as e to the arc cos of x sigma x, right? This is just a standard rotation case, okay? And the reason why it's written like this is because x is just some real number, arc cos will then give you precisely the angle. Okay, so our goal will be to generate a matrix whose entries are polynomials in x. So we want to have a matrix. We're starting off with something like this, but we want a matrix that in, let's say the top left corner will have a polynomial in x. And I should be able to specify the type of polynomial. And after doing my algorithm, I should get back that polynomial of x in the corner of the matrix. Okay? So we can do this by interspersing this wx or interleaving this with z rotations. So if we have a circuit which is defined like this, w capital phi of x. So, by the way, I should mention, I'm talking about signal processing. All of the symbols that I'm using don't have the same definition as the first section. They'll all be newly defined. So, we're talking about a new thing. So, don't get confused by the symbols. So, this phi is just a couple of functions phi 0 to k. They can be scalars, they can be functions which take input, but for now, just consider them just arguments phi 0 to k. And by interspersing these rotations, right, with these e to the I phi sigma z gates, we are able to do this. We can generate a matrix with polynomials. Those arguments are entries are polynomials of x. Okay? So for the most part, we treat these as just numbers, these phi 0 to phi k. And finding these phi 0 to phi k is very, very complicated. And on top of that, I think there's like a 20-page paper that focuses on something called the equiangular decomposition for finding these files. So there's a whole subfield of people working on efficient algorithms to just compute these files for specific cases of functions that you need to generate. Okay, but for now we'll just treat them as just files. And we can encapsulate the idea of quantum signal processing, this idea of having polynomials of X in your matrix, with the following lemma, which we'll call the quantum signal processing lemma. There's many variations of this because people sometimes do it. If you notice, I had W phi of X defined with sigma Z rotations. You can also do it with sigma X rotations. There's alternative ways to do it, but we're just looking at the sigma Z rotations. But the lemma is very, very simple, right? It just says that there exists some capital phi, which is just a real k plus 1 entry vector, such that this matrix here is what represents a W phi of X, and it's the matrix that's constructed from the circuit on the previous slide, which is just the W of X interspersed with Z rotation. But this is what we're saying. We're saying that the whole circuit gives you the output of this 2x2 matrix, where P and Q are complex polynomials in X. That's what this is, the space of all polynomials in X with complex coefficients. And these polynomials must satisfy the following three conditions. The first being that the degree of the polynomial P should be less than or equal to K, and the degree of the polynomial Q should be less than or equal to K minus 1. The second condition being that P must have a parity K mod 2, and Q should have a parity K minus 1 mod 2. And we say that even functions will have parity of 0 and odd functions will have parity of 1. You can remember what those are from first year calculus. And the last condition is that for any X in between minus 1 and 1, you must have this condition here. So it comes from unitarity of this matrix, but it's just that the absolute value squared of the polynomial X plus 1 minus X squared of absolute value squared of Q of X is 1. Comes from the unitarity of this matrix. Okay? This is the quantum signal processing lemma. And what it's telling us is that if I want to have a matrix that produces for me in my top left corner a polynomial of some number X, then it must satisfy, the polynomial should satisfy all these conditions. And using some other results, we can find the angles of those Z rotations, which will precisely give you this quantity. But this is the heart of the quantum signal processing algorithm. All it's telling me is that I can construct a quantum circuit that can implement for me polynomials of X in the quantum. Okay, that's all it's telling me. So the proof is very, very complicated. You can find it in here. But it's because it's if and only if you're going to prove it in the forward direction and in the reverse direction. And it's done both ways with induction and a lot of matrix multiplication. But you can look at that for yourself. Okay. And when we lift this decomposition to higher dimensional cases via cubitization, we want to employ a variant of this that relies on reflections. So not just rotations W of X, but we want a way to implement this that relies on a reflection operator, like we use reflections in aperture amplification. And what we can observe is that we can rewrite that W of X using Z rotations with angle pi over 4 and the following reflection operators, single qubit reflection operator. Okay? And what that does is we can rewrite our circuit W phi of X in the following way. So we can replace W of X, which is this, and you can see here we start off with the first term in the circuit, and then there's just products, which is just Z rotations interspersed reflection operators. Okay? And you can realize all the functions that I described in the lemma using precisely this circuit. So any polynomial P that satisfies those conditions, you can realize now with this circuit using the reflection operator. That's all we've shown. So now that we know about quantum signal processing, we have at least a basic idea of what it does. It's a way of constructing a circuit that implements a polynomial in X. Then let's talk about how do we extend this or lift it to the higher dimensional cases, right? Because it's not straightforward, because I just showed you how to do it for 2 by 2 matrices. It's good for a qubit, but what do we do? Usually we're not just simulating a qubit. So let's use qubitization. And qubitization effectively just allows us to map a high dimensional block encoding to a single qubit. And once we map it to that single qubit, we can do signal processing on that qubit, and that will give us the output, block encoded function. So what this does is, the only way we can do this is if we decompose our block encoding into 2-dimensional subspaces. So we take whatever our dimension of our space is, and we decompose it into a direct sum of 2 qubit subspaces. Okay? How do we go about doing that? So let's consider a block encoding U of a Hermitian matrix A. I told you block encoding for us is going to be mostly Hermitian. And then we consider the eigenvectors and eigenvalues of A. So will be the eigenvalue equation for A, where this is the eigenvectors and lambda is the eigenvalue. Then we'll define the following projector. And the projector, which is capital Pi, is just defined as follows. And it will be such that when I conjugate U by this projector, I precisely get back just the one term in my block encoding that contains A. But for the people among us that can see it directly, this tensor product here is nothing more than just A with the direct sum or the Kronecker sum with the zero matrix, right? So this is exactly, so the Kronecker sum, if you have 2 matrices A and B, you take the direct sum of them, all you end up with is just a block diagonal matrix with A and B on the diagonal. Okay, so you can see this, that this is just equivalent to this. Okay, so what we've done now is, instead of working with tensor products, we move to the direct sum. Now, if we define this new vector lambda as just being this 0, which is a single qubit 0, tensor to the eigenvector, we do this so that when we apply our conjugated unitary U to this vector lambda, we get back the eigenvalue of A as well as this, this vector lambda. So we found effectively the eigenvalues and eigenvectors of this new operator, pi U pi. Okay? So already this is where, and I mentioned that, this encodes sort of the spectral information. And this is why, if we can encode the spectral information of A, we can transform the spectrum of A, and we can effectively come up with our block encoding of our function of A. Okay? And then we make the following claim, which I'm not going to prove, but you can verify it for yourself very easily by just doing the multiplication, is that U will map the span of these 2 vectors to the span of these 2 vectors. And UDAG, of course, will do the reverse. You switch it around when you're using UDAG. But you can verify that U will take a linear combination of these 2 vectors to a linear combination of these 2 vectors. That's all that claim is doing, right? It's telling us what U is doing in this new lambda basis that we're going to use. And then we go ahead and we define a normalized version of this basis. We define the normalized version as follows. And then we can re-express this using the following. So we now have this U acting on the span. So we said that U will map this to this. So we can re-express our U acting on these vectors in the following way. And after that, what we end up seeing from this is that U in block diagonal form, is just going to be the direct sum of these 2 by 2 matrices, which transform between the basis of lambda and the normalized state. So all it's doing is U is just making these transformations. It looks complicated, you just have to follow the algebra. But all we've done is we've taken the operator U, and we've shown that U will now only act on 2-dimensional subspaces of our system. Okay? And the operators in the direct sum, so that the operator that U is decomposed into, they're all just reflections. They're all just reflection operators. So you see this is just exactly just a reflection operator, but it's a reflection in terms of lambda. Okay, so these are all reflections are lambda acting between the 2 bases, those 2 normalized states. That's all it's doing. We're reflecting about those 2 bases, the 2 bases, the normalized and the unnormalized. And to respect the invariant subspaces, because there will be some subspaces that are invariant under those changes, we have to alternate between applying U and U dagger. And we can consider the following sequence of operations, which will precisely be the cubitization. So if you look at the sequence of operations, you have some sort of rotation gate here, you have a unitary, another rotation gate, so on and so forth. And this capital theta is just again a tuple of angles, and K should be even. So with the appropriate choice of the phases, this sequence can realize the reflection-based quantum signal processing sequence. So when I showed you how to do signal processing via the reflections, this sequence here with the correct thetas will do the same quantum signal processing with reflection. Okay? And this U in between, because U is only acting on two-dimensional subspaces, this rotation gate is only going to be acting on one qubit, and the U is what's going to be acting over the whole space. So that's how we're able to only do the signal processing on the single qubit, but then have it affect our entire system. Okay? So what we can do is this U of capital theta will produce a block encoding of some polynomial of our operator A for any polynomial that satisfies those conditions in the quantum signal processing lemma. So if P satisfies all of the conditions that I mentioned before, this circuit here can realize P of A, okay? Or at least a block encoding of P of A. So if I want to implement the sequence, we need to use a pi controlled NOT gate. And what is a pi controlled NOT gate? It's like a C NOT gate, but the control is not on whether it's 0 or 1, but the control is rather, it's conditioned on the state of your main register being in the state projected onto it by pi. So it's conditioned on the state after you apply pi to your main register. Okay? And if we conjugate these rotations, if you remember in signal processing, we had a rotation, a Z rotation. So if you conjugate it by these pi controlled NOT gates with the ancilla initially in the state 0, right? If we do, and conjugating just means if I have this e to the phi sigma z, you put one a pi controlled NOT gate on one side, put another pi controlled NOT gate on the other side. It's sort of sandwiching. That's what conjugating is what I mean. However, in this case, it's emission, so you can sandwich by the same thing. But usually, if it's not emission, it will be like something times this Z rotation on something complex conjugate transform. That's what conjugating means. Okay. And this is where we get the idea. And after you do that, what you see is that those three gates together just effectively implements the following operation here. And all this is it's sort of a rotation about 2 pi minus 1. It's kind of like a rotation, implementing the following unitary operation. Okay. And this is where we get the name cubitization from, because all it means is that we transfer the information about the block encoding, which part of the block encoding the state is in to the qubit, so that when we perform the signal processing on the qubit, we effectively perform quantum signal processing in superposition on the high dimensional target space. So by encoding which part of the state the system is in on a single qubit, and by doing the quantum signal processing only on the single qubit, what we end up doing is we see that in superposition, we apply signal processing to all of the subspaces. And when we apply to all of the subspaces, we're at the same time, of course, getting optimality of taking advantage of superposition, but we're also only needing to do the signal processing transformation, which is already really complicated, only on a single qubit. We don't have to do it over the whole space. Okay? And then finally, this is just the theorem that states the signal processing algorithm with qubitization, is that if you have any polynomial of x with real coefficients, f, with a degree of d, and where the absolute value of f of x is going to be a half, whenever x is in between, or bounded above a half, whenever x is in between -1 and 1, and if we let u be a block encoding of the Hermitian matrix A as we did in the slide previously, then a circuit that gives a block encoding of f of A using d applications of u and u dagger and one controlled U gate. So we can have a circuit that will do this, right? So that's the main theorem for signal processing, and you can find it in that reference. Okay. And then lastly, now that we've just built up all the tools we needed, the Hamiltonian simulation part is now very easy. And in fact, in most literature now, because of this optimal signal processing and cubitization algorithm that they have, if you can find a problem that you're trying to solve and you map it to some Hamiltonian, people most of the time now just say, we employ quantum signal processing and cubitization to simulate this Hamiltonian efficiently. And they end up the story there. But how do you go about doing that? Okay, so once we have the efficient block encoding of a sparse Hamiltonian H, okay, so where we use A before, we're going to put in our Hamiltonian H, and we scale it by the sparsity. So sparsity is a scalar number you can compute from H. It tells you how sparse the matrix is. We scale this H by the sparsity, so you're doing a scale block encoding. And our goal is to turn this block encoding into the encoding of the evolution operator. So we started with H being block encoded, and we want to figure out e to the minus IHT. So you want at the end of it, you should have an operator that'll do e to the minus IHT, okay? Or at least something that's approximately close to that. And we can do it using the Jacobi-Anger expansion. So what is the Jacobi-Anger expansion? It's just a way to represent exponential trigonometric functions in terms of their harmonics. Okay? It's used very commonly in physics, and I'll tell you where they use it in physics as well, in signal processing, in understanding FM signals and AM signals. That's also where the name comes from, right? So when they did signal processing, this is what they did. Okay? So here, this is just a way of expanding e to the IT on cos theta. So once you can expand this e to the IT on cos theta, we see here that it's given in terms of Bessel functions and Chebyshev polynomial. Okay? So this you can find on Wikipedia. It's nothing like complicated. I just show you how this Jacobi-Anger expansion works. Right? And then by truncating the expression to the first capital K terms, we get a k degree polynomial in X. And this k degree polynomial in X is, if you look here, this k degree polynomial in X is approximately equal to e to the minus I t of X. And if X is going to be precisely the Hamiltonian, then we have a way to approximate the Hamiltonian by some polynomial. Okay? And using this polynomial, but scaling it down by 2 because we need this polynomial to satisfy the conditions in our theorem, then there will be an efficient block encoding of H. So there's if U is an efficient block encoding of H, then we can get a block encoding of e to the minus IHT over 2 using only K applications of the U and U diagram as per the theorem that we have. And we can then study the complexity, but of course it's very complicated. There is the 2 papers that I'll point you to go look at the analysis, but we can just talk about what the error is and how does it scale. As you can see here, the details is omitted because it's not illuminating. It's just the same stuff we did last week with a few more complicated expressions, right? The main idea is what is the error mean? The error scales T over 2 to the power K all over K factorial. So if we want to simulate this to a precision big O epsilon, it suffices to choose K right after we solve that using some approximations and Stirling's formula, Stirling's approximation. We see that K, it's fine to choose a function K that's bounded that bounds above this function here. So we see a linear in T, so linear in time complexity, and instead of it like the truncated Taylor series where it was multiplied here, you see it's added now. And that's a lot better because adding 2 numbers goes a lot smaller than multiplying 2 numbers. Okay, so if we have a linear in T complexity scaling, and we have this logarithmic scaling with respect to 1 over the precision. Okay, and this is a tight and optimal bound for simulating Hamiltonian dynamics. And I think these papers show you how this is the most optimal method to simulate Hamiltonian systems. Okay, I'm sure there's other ways that people have looked into speeding even this up. But in terms of finding something more optimal than this in the T complexity, you're not going to, because you've got linear complexity in T is the optimal bound. So when they talk about this is optimal, it's not the whole thing, but just optimal in T complexity. But logarithmic scaling and precision is also very, very good. It's what we want when we're doing simulation. Okay. And again, how does this compare now to the other methods, right? Why is this considered optimal? But let's have a look here very carefully. We'll see that for the same parameters that we used before, let's just put signal processing back on the plot. And we see here that in the beginning, it doesn't perform as well as the Taylor series, but that's because of the Taylor series and the signal processing, they have time scales at which they're applicable. But we see that after this point of time here, which is like around just say 1 second or so, the signal processing is just outperforming it completely. And this is optimally typed. So you can see it outperforms the product formulas, it outperforms the truncated Taylor series, and quantum signal processing is the optimal. Of course, if you change these parameters like epsilon, you'll see even better scaling in terms of the quantum signal process. But that's just something I wanted to show you, that this is an efficiently scaling algorithm. So yeah, I think that's all I want to talk about. Of course, with caveats, as I mentioned, there's so many caveats, but that's all I want to talk about here is just these two algorithms. And next week, we move on to talking about the quantum simulation of open quantum systems, which is where I work and do my research. Yes, thank you.
Let's check. There's a Q&A
question here in the chat. How is there a tensor product between a bra 0 and what looks like an identity? Well, we can do that because that operation is just telling me that I want to post select and just measure only the first qubit. So when I construct the measurement operator, I want to perform a measurement that only tells me when the state, the first register is in the state 0, but I still want to keep the rest of my states afterwards. And you can think of this as like kind of just partially tracing out only the first qubit, but I'm not summing over all the basis states. But it's just constructing a measurement operator that will check when the first register is in the state 0. And what that'll do is after measurement, my system, I still want to see what is the state of the second register after I've made that measurement. So that's why you have 0 tensor identity, the bra 0. This is a common thing in quantum computing.
That was in Q&A. Is there anything in the chat? Okay.
Could you provide an example of how quantum simulation has provided new insights into a specific area, such as many-body physics or quantum chemistry? Okay, so here the discussion becomes a bit tricky because the algorithms that I'm presenting in this course are suited to the fault tolerance setting, meaning that we can't run any of them on modern devices, right? But when our device hardware catches up, these algorithms are going to provide us great insight into simulating physical systems. However, that hasn't stopped us from using NITheCS devices to gain better insight into into simulating systems. So for example, while you wouldn't use Trotto Suzuki to do the simulation, there exist algorithms like the variational quantum eigensolver, which is using a quantum computer to find the ground state energy of a specific system. So while the quantum computer is not directly simulating the evolution by something like Trotto Suzuki, we're using a variational quantum algorithm to obtain the ground state energy of molecules and things like, things that people do in quantum chemistry, where they find the ground state energy, which is, of course, a large part of that. Studying many-body physics, the goal right now in Hamiltonian simulation is to develop efficient tools and methods to solve these problems on quantum computers. So let me give you an example. For the most part, the systems that we will consider are simple systems, like spin systems, okay? And spin systems are nice because we know how to construct gates and operators that can implement, e to the minus I, h, j, t on a quantum computer. However, what happens when we talk about infinite dimensional systems? So you talk about things on infinite-dimensional lattices or even just optical systems, like quantum optical systems. Problems immediately start to arise when you need to truncate these types of systems. And people have been working on developing algorithms to represent, study, and simulate these Hamiltonians using the methods that I'm mentioning here. And they currently only do, numerical experiments to show it. But once the device hardware catches up, we'll be able to use these algorithms to give us better insight into physical systems by simulating them on a quantum computer rather than implementing them, or rather than trying to build an experiment that realizes them in a lab. A large chunk of work that's currently going into this field is trying to simulate field theories on quantum computers. I think only recently they've developed an algorithm to simulate the path integral on a quantum computer. If you've done any quantum field theory, you know that second quantization has so many limits, and you'd need a quantum algorithm to simulate the path integral on a quantum computer if you want to realize the simulation of these types of systems. So while there is not much that you can do with these algorithms to simulate physics on a quantum computer now, there are alternative algorithms that are more suited to the NISC era that will allow you to gain insights into these types of physical systems. As I said, like the variational quantum eigensolver. I think if you look at also the Quiskit tutorials, they have some very basic Trotter-Suzuki implementations on their hardware. But as I said, the hardware is not caught up. If the last lecture I showed you how many gates you would need to do a simulation for a very small system, a simple four photon Hamiltonian, how many gates you would need to simulate that. It looks something like, I think, 52,000. I don't think our quantum computers, as of yet, our quantum simulators have reached that capability yet. However, if you are interested, there's things like D-Wave, which are not universal quantum computers, but people have been using quantum annealing to do things like simulating protein folding and other types of systems by using the cubo-Hamiltonians and stuff like that. But for the most part, I'm talking about the algorithms and methods that are suited to fault-tolerant setting. And hopefully one day we'll use these to actually gain some understanding of real physical systems, while now by making arguments on things like complexity and complexity, scaling, and precision, we can theoretically predict how well our algorithms will perform on specific types of systems. So there are people who take these fault-tolerant algorithms and they apply them to specific Hamiltonians to look at what the optimal performance will be. There's a paper which I'll include in a slide before it goes up, which is Hamiltonian simulation with optimal dependence on all parameters, and another one which is towards the first quantum simulation with quantum speedup, where they study just the Heisenberg model. And they try to see which algorithms are under which setting and on what type of quantum device would we need to be able to do a quantum simulation of a simple thing like a Heisenberg chain. So I hope that answers your question.
Okay. And are there any other questions? Is anything in the chat? No. Okay. Thanks. Okay. So I think we can wrap up for today. Thank you very much, Ian. Yes, I'm taking into account that we need a bit more time. I hope to see all of you next week for the continuation of the story when we're going to dive into the quantum simulation of open quantum systems. Thank you very much.